Hello, today 405 line. Now for viewers outside of the UK, just a quick bit of introduction as to what this is. This is an early monochrome television standard, and there were a number of others like it which were used in various places around the world. Now I suppose what's significant about it is that it is completely incompatible with the more modern 625 line system which was used in this country. But nonetheless, what's quite notable about it is that there is still quite an active community of people who do various things with it. For example, here on YouTube alone, there's a couple of channels where we can regularly see 405 line equipment being repaired and demonstrated. On the broadcast side, previously we talked about Brian Summers. He runs a project which basically maintains a 405 line capable outside broadcast van. And there is an equivalent van up in Lincolnshire with the BECG. Now, unfortunately, I did take some footage of that when I was up there last, but I seem to have since lost it, sadly. But that is also out there. Now, one of the things that's a bit frustrating about 405 line is that because it is incompatible with any other standards, it's a bit tricky to find equipment which is actually capable of creating 405 line signals, both at the baseband level, so your test pattern generators, but also modulators. That's not to say there's none of it out there. Of course, there is a whole range of homebrew projects where people have built all sorts of amazing things. So test pattern generators and modulators, and the people who have built this stuff really show that they have a real detailed understanding of the television standard in question, but also in electronics, and I find some of it really amazing. So what we're doing in today's video is to think about this from my perspective. So let's suppose you've got all the gear and no idea. What sort of demonstration could we put together? Now today's demonstration is mostly going to be centered around the Snell and Wilcox TPG21, which we looked at in the previous video. We found a test card F version of it, which was just amazing, and I still can't believe that that's something that I actually physically had here, and it is still here because the power supply blew up and I'm now waiting for another one, so we've got it for a few more weeks. But anyway, since that last video, myself and a couple of others have been looking closely at this product, and we found some quite interesting things about it. Notably that in addition to supporting all of the common types of PAL, such as PAL-M, PAL-N, and just regular PAL and NTSC and all of that, it actually supports a whole bunch of other television standards, or when I say supports, it looks like Snell and Wilcox at least did some work on some other more obscure standards. So, for example, the Japanese high vision system, that's a 1125 line, and also the Eureka 1250 line standard, also known as HDMAC. And we even found some code in there for 405 line, which is quite surprising, because that would have been turned off back in 1985. This product didn't come to market until 94, we don't think, so it's quite surprising to see that they actually did some R&D on this. Now, this having been said, all of these unusual modes, none of them appear to have been completely implemented. They're all, you know, a bit of it here, a bit of it there. It doesn't look like they actually finished any of it. So that was really kind of the basis of today's video. We just wanted to pick one of these unusual modes and see if we can finish it off and see if we can get it going. So of course we've chosen 405 line for the reasons that I just mentioned, because it is still quite an active space. So let's have a look. The 405 line effort begins with the Pattern Master software, which I mentioned briefly in the previous video. Now this software seems to be somewhat long lost. Looking around the internet, there were quite a few people who have been looking for it to no avail. We actually found a copy of it in the Quantel community, which is fantastic because we may have never actually seen this otherwise. Now I have to confess up front that I'm not an expert on this software. Most of the work here has been done by the TCF generator owner Steve, who has spent quite a few hours trying to make it behave, and it hasn't been too difficult because it does actually play rather nicely with 405 line. Now he sent over a number of examples for us to play around with. So this here is a multi-burst, and you can see that it contains all of the features which are output, so not only the visible area but the blanking area and also the sync periods as well. These are appearing in this yellowy greeny color. Now this is a line type test card, which means that all the lines are the same, and it will have been defined by a formula which in the software has then generated all of the appropriate samples, which is certainly best practice for software generated test cards. You don't want to be using graphics editing software, certainly not for something like this. Now, in addition to this, we also have a staircase, so just a grayscale staircase, just another test one that we played around with, and it's a similar deal, line type, all of the lines the same. So when this is written into an EEPROM on the unit, it would take up very little space because everything is just repeated, because they do have a form of compression which handles that, which is really good. Now we do have another interesting test card to play with, which is test card D in this format. This one here is a bit different. So this one has not been defined in the software. It's actually been imported as a computer graphic. And this is the computer graphic in question. Now, importing from computer graphics has a number of problems attached to it. The first of all is, well, if you look at it here, it's quite stretched, so there's had to be some scaling going on. And also you have to think about what is the actual bit depth of this. So the unit is capable of 10 bits, whereas a Windows bitmap is only 8 bits per channel. So straight away we lose that nice premium feature that this unit has because we've used this rather rubbish file format. But that's not actually the major problem, because 405 line equipment is not really very accurate, so I'm not going to worry too much about that. The real problems is when we start thinking about the scaling that has to happen here. Now, the reason that it is so wide is because each line contains 1,280 samples, and that's as a result of the 12.6 megahertz sample rate, which Snell have specified for 405 line use. We don't know where that number comes from, that's just what they have here. So when we look at the bitmap, it's completely the wrong dimensions. So if we actually look at it, it's 640 wide and 468 high, so yeah, that's not appropriate for 405 line. However, it doesn't actually matter all that much because we can scale it very nicely. The main thing we really care about at the moment is the width. So at 640, I haven't done the math, but that's going to be well above Nyquist in terms of the sampling. And because bear in mind that we only have 3 megahertz of video bandwidth here, realistically. So yeah, that's going to be comfortably above that. Height's a bit of a problem, it does have to be scaled, but the Pattern Master software will do all of that nicely. So let's have a look at some of the problems with scaling. So if I actually just go and do this in Paint, so we'll whack in 200% here. There it is. So if we have a look at the frequency gratings here, these lines on the more high frequency ones, well, they start off quite thin, then they get thicker, and then they start getting thin again. And this one here is kind of alternating between thick and thin and thick and thin. So basically the problem here is that the scaling algorithm that's used by Paint, and certainly a lot of other graphics editing software suites, it does this using a more kind of visual approach, which is not really what we want. Now, if you actually went and zoomed in on it, you can kind of see, where is it, why it's done that. So if we go large size and scroll down, yeah, so the lines, although they look nice from a distance, when we look up close, they're not actually all that great. And however, if you turn this into an analog signal at the appropriate sample rate, it would actually make a perfect sine wave. So what we really want in our scaling is an algorithm which behaves more like an analog signal path. And that's exactly what the Pattern Master software has. So when it imports a bitmap, it uses a finite impulse response type algorithm to scale it. So we actually have a perfect grating there. So when this is actually turned into an analog signal, it will look just fine. That's because the algorithm is treating this as if it is an analog signal. So there's just a little thing to consider if you are ever mucking around with test cards in graphics editing software. Don't do it unless you want to end up with garbage. Now there is also the matter of the height, and I presume that the import process has also taken care of that, but I don't know because I haven't looked at this personally. Now from here, we can actually switch on the generator and start thinking about uploading it. In the transfer menu, we have 2 options here. For TPG 20 owners, you only have one choice, which is frame. And this is going to upload it into those SRAM chips, which the DACs render out of. When you turn the unit off, it will be lost. For TPG 21 owners, you have an additional option here of this EEPROM option, which allows you to program it into one of the non-volatile slots. Now we're actually presently connected to the test card F generator, which is a TPG 20. Now, this dialog will actually work. It's going to show me all of the test cards which are in each slot. They seem to break it up into 5 1 megabyte PROMs, which may be implemented by 2 half megabyte PROMs. So if we go to slot 3 I believe we will have, there it is, there's the test card F EEPROM there. But in all cases it'll say EEPROM not programmable, so this dialog is not usable for this model. But what we can do is transfer into the frame. That's going to work just fine. This goes over the parallel port. And from there, I thought that we'd be up and running. That would have a nice 405 line signal coming from the output, but we did not get any such thing. I did briefly see the signal I was expecting on the oscilloscope, but it quickly faded to the maximum possible DC level of the output, which was kind of weird. So I went straight to the output section of the schematic, and the problem was immediately clear. We can see that there are 3 transconductance amplifiers on here, which indicates that this design uses a timed DC clamping circuit. And there is the signal right there. So what's going on? Why isn't that being driven correctly? This is the section of the schematic where that's actually coming from here. So from these 2 programmable logic devices, H counter and line counter. Now what we found from a bit of reverse engineering is that these support up to 8 different video modes, and we know what all of those are, and unfortunately none of them are 405 lines. So the deal basically is that these do not implement the relevant timing signals for 405 line. And it isn't just the clamping signal, there's various other ones which are important, such as the terminal count and the vertical clear, and these will be driving the sequencing as the unit iterates through all the data inside of the SRAM chips. So what to do about it? Well, of all of the modes that it supports, one of them looked like a good candidate to overwrite, and that is the Japanese high vision system, which does appear to occupy quite a bit of code in these devices, and it doesn't appear to be completely implemented anyway, so we don't mind getting rid of that. But in order to do that, it's quite difficult, because the ATV750 is quite an obscure device. We can read the fuse map out of these chips, but unfortunately we can't turn it back into a list of Boolean equations, which we would need to be able to do to attack it and actually modify it, because the tooling just isn't out there. So what to do about that? I thought that in this age of generative AI that this wouldn't even be a problem, and I even asked ChatGPT if it would be able to decode an ATV750 fuse map for me, and it assured me that it should be able to do a pretty good job of that, so I tried it. And 25 minutes of huffing and puffing later, it eventually came back pretty much empty-handed. And I'm not going to rerun that just for your entertainment, because that probably used a hell of a lot of electricity, and that electricity is not being generated renewably. So what's the problem here? Well, I tried a number of different LLMs and all sorts of experiments, and it seems to be basically that they just don't understand the ATV750's fuse map, and it's not something that is really ever discussed in textual form on the internet, because it's quite an obscure device which nobody really cares about. But it is all explained in this diagram here, and the fuse map actually overlays perfectly onto this. So if you look at the file and you connect the lines together, you can put together the logical equations fairly easily. But you do also have to take into account this diagram here, which explains all the ways that the macro cells can be configured, and this does have a significant impact on what you actually end up with. And connecting these 2 diagrams together does take a bit of extrapolation, and it's not entirely obvious when you first look at it. So it does appear to be a case of a highly advanced technology encountering what to us humans is a fairly simple obstacle. And I guess it shouldn't really be surprising that it can't do this, because this is not a text prediction job, and text prediction is what LLMs do. Realizing that I was wasting natural resources, my time, and somebody else's money, I decided to create a deterministic model to decode these fuse maps. Deterministic model being an AI industry term for doing it the old-fashioned way. And it turns out we don't even really need to do the full job. The main project actually contains a utility called JEDutil, which is an open source tool that is actually able to reverse the fuse maps for quite a wide range of old programmable logic devices, but unfortunately it doesn't support the ATV750, so we would need to add it in there, which in theory shouldn't be all that difficult. But there is one slight problem, which is that the ATV750 has this concept of combined or separate terms, where you can basically join the p terms from one macrocell with another, which is a really powerful feature, but yeah, JEDutil does not like this, and I had quite a job trying to hack it to accommodate this. But I eventually got there, And I was able to accurately regenerate the Boolean equations from the code that I dumped out of the chips. From then, probably a few hours later, I was able to reconstruct very nearly the original Snell source code for the devices, which allowed me to actually get on with the job of adding 405 line to these chips. So all of that nonsense aside, what are we actually trying to do here? Well, this is a 405 line monochrome waveform from an old BBC specification. So in addition to counting to the right number of samples and lines so that we can reset the digital circuitry at the right time, we also have to generate that clamping signal, which I talked about before. The basic idea is that suppose this is your dynamic range, your sync tip from the white level, 1 volt from end to end, and you've got this 300 millivolt offset. Now you don't necessarily want to be nailed to that offset because let's suppose you want to support a different standard like Mac, which is symmetrical, so you want to have a different offset. The way you do that is you clamp at a part of the signal which you know is what you want to call 0 volts. And in this case, it's going to be the back porch. I could also use the front porch, but yeah, it's kind of puny in 405 line, so we'll stick with the back porch. Now for PAL, it clamps in the middle of the color burst, which is kind of weird, but on average it's 0 volts, so yeah, that's fine. So what we have to do is basically time from the starting point, wherever that is, to where we want to assert the clamping signal, and the horizontal counter, which is in one of these ATV 750s. As I say, if we overwrite the high vision entry, we do have enough space to implement that just fine. The difficulty comes in with the vertical counter. So in addition to clamping at a set period on each line, we have this slight problem here of the horizontal sync period, the vertical sync period, where the polarity inverts. And if you keep clamping in here on the same intervals, you end up clamping at this low level here, which is going to be negative 300 millivolts. And what that's going to do is it's going to basically shift the whole level upwards a little bit. So we have a little bit of an error in here. And it's not going to be very much, but if you know there's an error in the signal, then it's not a test signal anymore. It's just a signal. So that's not tolerable. So we also need to have basically a big pulse that goes low during this time that we can end the clamping signal with so that we don't clamp during here. And these are implemented for the 525 and 625. They use the D1 blanking signal for that, which is a much larger pulse. It sort of starts maybe over here and then goes all the way over here. It's far bigger than it needs to be, but it does the job. Now for 405 line, we can't really define a sensible D1 blanking signal because we would need a spec for 405 line SDI, and there's no such thing. So what we really want to do is just have a pulse that asserts during this time so that we can turn off the clamping signal, which sounds easy in theory, but in practice there is a slight problem, which is that clearing the high vision code for the vertical counter doesn't give us enough space to implement what we need in here, which is it's a real pain in the ass. So what I had to do is make up this little board here, which has got two ATV 750s on here. So this is the new vertical counter, and it just plugs into the socket of the one that was there. So basically I've split the code across two different chips. So this means we can support 525, 625, and 405 all at the same time. We don't have to go swapping out chips and all that nonsense. So that's pretty nice. And it has to be the 25 nanosecond ATV 750 as well, just to be extra annoying. I don't know why this is. I've tried 10s, I tried 15s. They don't work. Well, they kind of work, but they're really unreliable. Has to be a 25. I don't know what the deal with that is, and quite frankly, I don't really want to know. This works fine, so we can get on with it now. So just a few extra things to cover before we get started. Now, as I mentioned before, we do have this extra crystal frequency of 12.96 megahertz. That's that one there. And this is not something that comes with the TPG21 as standard. It has to be added. Normally, this position here is unpopulated, and the deal is that you can add an extra crystal of your own choosing, and it can be used for a variety of different things. So at the moment, we have 13.5 megahertz, which is that's your kind of D1 type standards, and then 17.734, that's PAL 4FSC, and that's the NTSC 4FSC. So if you wanted to do PAL N or PAL M, then you would add another one in here, and you've only got one option. So what we've done, as I said, is added to the 12.96, which we're very fortunate there was actually a source for those crystals, because that's quite an unusual frequency. And once that's been added, there's a few extra changes. So I had to change some of the passives around it, some surface mount components under the board, and also that inductor, and tune this variable capacitor here, basically just to get it oscillating at exactly the right frequency. So that's all done. And once that's done, we then have to map this crystal slot here to the 405 line mode in the service menu, which is pretty easy. Now the next thing, of course, is replacing all those PLDs. So we've actually replaced 3 of them. So that's the horizontal counter there, and that's the vertical counter that I talked about, which is now split across 2 PLDs, and there's another vertical counter here. And there's actually another vertical counter here, but this one we don't need to worry about because it's just generating a burst gating signal, which is used for genlock, and 405 line genlock is not something we're really trying to get going here, and there's no burst to gate even in that mode anyway, so yeah, left that one alone. This one, yeah, this one's generating like an odd even field signal. Not sure if that's actually used, but I did modify that one and reprogram it, so that's all done. And the other thing that I did here is something I promised I was going to do. This unit, the test card F unit, the selection of Snell test cards that it came with was rather disappointing. So I took the 4 megabit EPROMs that it came with out, and then we now have another 8 megabit EPROMs in here, and we are loaded with Snell test cards in here. So I think our owner is going to be happy with that, because this is actually what he bought the unit for. He wasn't really specifically looking for test card F. But before we power it on, there's one last little thing that we're going to do, and that is pluck out the Snell number 2 EPROM for 525 line, because we don't need that. And what I'm going to put in there instead is something very special. So I've got a test card D EPROM here, which I prepared earlier. So let's chuck that in that socket. And let's take it over to the bench and fire it up. So here is our test setup, and we're using this lovely little dual standard Sony set, which was loaned to me by Andy from the Robust Reviews channel. He even delivered it to my doorstep, which is pretty good service, I have to say. Now at the moment we are looking at test card F in 625 line mode, and that's getting to the TV via this cheapy consumer modulator. This is a pretty common thing that people do with these sets. It's basically the only way to get a signal into them because they don't have a baseband input. Now, just looking at this test card, it's kind of interesting. The black bar on here seems to be creating some skewing of the, I don't know, maybe there's some kind of term for it. I don't know anything about CRTs, but yeah, this doesn't look all that great, if I'm honest. So let's see if we can get it into 405 line mode. So what we've got to do is press the format button, and then we can go through all the various options, and we will eventually see a new option. Ha ha! Look at that, 405. This is one of the things I just love about this bit of equipment. We didn't have to do any hacking whatsoever to get a new menu option in there. It just appears. It just, the unit knows that it's got a new standard, and you have a new menu which we can use to filter all of the available test cards in that standard. And presently that's just one in the others menu, and that is test chart D, sir. Now, I'd love to tell you that was original Snell, but I typed that out myself, unfortunately. So let's select that one. So, at the moment, we're receiving a 405 line signal when the TV is expecting 625. So this is what you get. Now, I'm told there is a little cheat mode where you can get the set into 405 line mode on UHF system I, which this modulator is capable of. So you have to push both buttons in. Hey, look at that. And there it is. Test card D coming from the Snell & Wilcox TPG21 405 line. It is just a really fantastic thing to see. I have to say, it is so satisfying for me to be witnessing this. I know it's completely useless. It's you know, there's various other ways you could do this, which you know, involve significantly less effort and expense and what have you. But it's just really interesting to see it, because the only reason that this is possible is because Snell & Wilcox have already done a lot of work on this. You know, the thing fundamentally does work with 405 line mode. It's just the code in those damn PLDs which is missing, and it's taken me 2 weeks to figure out how to add it back in there. And maybe there was some version of those chips which does natively support it, but we just don't have that here. I'm not sure if it was the case that we'd probably have to sacrifice 525 line mode, or have some kind of bodge board like we've got in here. Anyway, so we've completed part one of our professional 405 line setup, and it is looking very nice. The picture looks actually much nicer than it did the test card F. It's that stripe thing I was showing you, it's not there. It all looks really lovely, really nice quality. Now I'm expecting on our System A setup it's not going to be as sharp as this, because we have actually 6 megahertz of video bandwidth available here, which is, yeah, that's quite a bit more than what we're going to have with System A. It's going to be only be half that. So I'm expecting this to be a bit fuzzier, but let's get into it and have a look. Before we can create a System A transmission, first we have to understand what we're actually trying to do here, and that includes me because I've never even looked at this before. Now the first thing that really jumps out about it to me is that the channel actually extends downwards from the center frequency, whereas normally for all the other systems it's the other way around. It's a vestigial sideband, but the vestigial is the upper sideband, so it's the lower that's actually complete. So it's just, you know, that's quite odd. I've not seen that in any other system. The audio is AM, and it's at negative 3.5 megahertz. Once again, that's kind of odd because all the other systems it's positive. So the whole thing is kind of backwards. Now this is immediately problematic for the sort of equipment that I have here, because it's all designed to have this the other way around. So one way I could tackle this is to add an extra heterodyne conversion stage to flip it over at the output, but that's going to be some kind of contraption. It's not going to be very pretty. It's not going to be professional equipment, which is that's the requirement I'm setting myself here. Now we do actually have a fortunate bit of luck in that the fabled Crystal Palace transmission, which seems to be very sacred in the 405 line world, apparently that was actually a double sideband, which is like, yes, that's a lot easier to deal with. So basically, I can just modulate both of them and output it, and that's going to be fine. But there, of course, is the other problems to deal with: the modulation type and this audio. Now it happens that we do have a useful starting point here, and I think my more expert viewers are immediately going to know where I'm going here. So what we can do is set up my PM5680MS in the French System L mode, and it is worth pointing out that it is only System L if described in the appropriate language, which does have a lot in common with System A. It is positive modulation, like System A. It has AM audio, like System A. But unfortunately, that's it. The rest of it is quite different. So the channel extends upwards from the center frequency, annoyingly. But as I said, that's not going to be a problem because we're going to use a double sideband. And the frequencies are all quite different. So these channels are much larger. The audio carrier is at the wrong offset, so probably can't really use that. Or maybe we can, not sure. One of the, I think, other issues which is less obvious here is that our video bandwidth is 0 to 3 megahertz, and we're going to have an audio carrier somewhere here. But the modulator is not going to have a filter to constrain the bandwidth of the video signal to 3 megahertz. So if it was containing anything above 3 megahertz, that's going to go in and interfere with the audio, and that's going to be a bit annoying. I don't really have an easy solution to that problem. It's just going to have to be very, very clean. So I think we've got a starting point here. So we go and put the modulator in System L mode, and we should reasonably easily be able to get a picture. So yeah, let's go and give that a go. To get a usable System A vision carrier out of our 5680MS is actually pretty straightforward. So let's run through it. First of all, we'll switch it on. That's presently in System I mode, which is UK color. So we switch it over to System L. That's French color. So now we have a positively modulated AM VSB signal coming out of it, which is a good place to start. There's a few other things we have to change. So we have to turn off the VSB filter, so put it into double sideband mode. And we also have to turn off the sound carrier, because an AM sound carrier at 5.5 megahertz is not much use. And then the modulation depth. Now, presently it's set for 20%, so that means we have 20% margin for chrominance. Presumably you would just crank it down to 0% for System A. I don't know why. I certainly don't see any reason why you wouldn't. Correct me if I'm wrong about that. The last thing which is worth noting here is that the sync LED is switched off, and what this is saying is that the modulator does not recognize your incoming signal. Now that doesn't mean that it's not going to modulate it, but what it means is that the DC clamping feature, which this normally has. If you don't trust your DC levels, it can actually restore them. That's inactive and unusable. So your DC levels have to be correct when you're running in this mode. Now the next thing to do is switch on the 5690, which is going to get us on channel. Now I've actually already got this set up. That there is VHF channel 3. And I just picked this one because I had a bit of a nightmare trying to align the TV with the output of this. The tuning in this thing is just, I have no idea, there's no labels on it or anything. But anyway, this one works, so we'll just stick with that. Now an interesting feature of System A is that it exclusively occupied VHF in the UK, so you would never ever receive colour television on VHF, which is, yeah, certainly from where I come from in New Zealand, that's quite odd. We did have colour on VHF, and I think a lot of other countries did as well. So, yeah, this is quite unusual. Anyway, so let's switch on the telly and see if we can see a picture. Right, so we got to push the VHF switch, which for this UK model of set just automatically puts it into 405 line. So there it is. Looks pretty nice. As I expected, it's a bit fuzzier, so those higher frequency gratings, from memory they were quite clear before, now they seem to be a bit fuzzier. Now I think it's actually the TV which limits the bandwidth to 3 megahertz, because this modulation setup, definitely there's no limiting on it, so it must be happening in here. Now in terms of our audio, we've got, ooh, that sounds kind of nasty. So we've got, yeah, rather unpleasant sound there because we have nothing. What we should be hearing there is static, but this indicates that we have some video noise, so yeah, that's not ideal. Our next job is to set up some audio, and we're going to be using this ESG signal generator. Now we could probably modify the Philips modulator to generate negative 3.5 megahertz AM audio, but I'd rather leave it alone because it's quite a rare and vintage item. So we'll run through and do it on here instead. But before we get started, let's just have a look around the back and see how this is actually connected into the setup. On the back of this unit we have just 2 RF connections, so there's an IF input and RF output, so that's going to be our final television signal on channel. So to add in the System A sound carrier, we're going to be using a technique which I've used before, and basically in exactly the same way. So we've got a directional coupler on the back here, which I normally use for adding NICAM into the IF signal. So the deal is you connect the vision modulator to this input here, and that may contain FM audio, maybe not. That just goes straight through, and then we then connect the IF output from the NICAM modulator into this connection here, and this is combined directionally onto the vision carrier. So the vision goes straight through and the NICAM is combined on in this direction. It is not allowed to reflect back out of that port there. So basically we're just doing exactly what we did with the NICAM modulator, except it's AM audio instead of NICAM. So we're presently in the default unconfigured state. Let's run through it. First of all, let's pull up the AM modulation menu. Now we're going to turn on our AM, just one carrier. Our modulation depth I'm going to set to 100%. I don't see any reason to have anything less. And our source is going to be internal. Now we do on this unit have the option of an external source, so you can feed in a baseband audio signal into these external inputs and it will modulate it. I've tried that, it works really nicely, but we don't need to bother right now because I've got the baseband generator option installed in this unit. So we can just set a tone right here, which is going to be 1 kilohertz. And I think that's all we need to do in the AM menu. So next thing is the frequency. So we're going to set it to 42.4 megahertz. Now this is the IF frequency, which is 38.9 plus 42.4 equals 3.5 megahertz. However, because this is an IF and it's spectrally inverted, that's going to end up being negative 3.5 megahertz. Next up we set the amplitude, and this is going to be to negative 27 dBm. That's the number that I just found by experimentation. Works really nicely. So we're now ready to switch on the output of this unit, and we should see it on the spectrum analyzer. Hey, there it is, look at that. Now what we're seeing right now is the double sideband from the vision modulator plus the AM audio from this signal generator on channel. Now just for interest's sake, we can turn off the VSB filter, and we can see we suddenly lose a whole lot of information from the sideband that we're actually using on the vision carrier. So yeah, we don't really want to do that, so we'll leave that switched off. Alright, let's go and switch on the telly and see if we can hear any sound. Well, our picture is still looking pretty nice, which is that's a good start. Let's turn up the volume. Hey, 1 kilohertz. Sounds lovely. I don't normally enjoy that sound, but I'm enjoying it today. Alright, so let's switch off the audio again and listen. So straight away you can hear this vision carrier is coming out of the speaker, which immediately highlights the problem with this setup. Now we can see what's going on there by turning off the or turning on the VSB filter. So let's switch off the audio carrier again and put it into VSB mode, and it goes away. So that kind of tells us what the problem is here. This is something I talked about earlier, where if the video bandwidth is exceeding the 3 megahertz, it's going to go and interfere with the sound carrier, and it is. So what this tells us is that our test signal coming from the Snell Wilcox is containing components which are exceeding 3 megahertz, and we know it is because we know that the VBI needs a bit of optimizing, which is that's coming in future. But for the time being, it's not perfect. So there you go, there you have it. And I'm not going to pretend that this setup is somehow superior to the homebrew, 405 line test pattern generators and system A modulators. They're probably way better than this. This was just a kind of fun experiment, and we probably could improve it with a bit of tinkering. But anyway, I think we broadly achieved our objective for, for this video. Well, that is it for today, and I'm sure there's some more fun to be had in this space in the future. Now, as always, all the work that I've done on this, I will make it publicly available on my GitHub, so if there's any TPG 20 or 21 owners out there and you are feeling like going down the frankly ridiculous path of making it 405 line capable, check out the link in the description, and if you have any troubles, let me know and I'll happily help you out. But anyway, that is all for today's video, and thanks for watching.